Hello, relativity friends. I got a really interesting question from a very observant viewer. They said, "Why can't I use the formula for the Ricci, the tensor, which is given as this, instead of first of finding the Riemann, the tensor, which is the traditional way? Is you find the Riemann tensor first, you contract it to find the Ricci, the tensor. Now, this format here is the contractions already built in. All right, so this is from the book. That's where they saw it, and I have these books. General Relativity Intuitive Introduction by Ville Hervoven from Profound Physics website. He has it listed like this. I just took a picture of it. Okay. Now, if you look at this thing here, there's only two free indexes here, and everything else is a summation index. So these are here's a double sum, here's a double sum, here's a sum, and here's a sum. I mean, it's a lot. There's a lot going on there. There's 20 something terms or something. I don't know what it is. So the question is, why do I have to go through all of this? Do you remember when we did this for the two sphere problem? We took the generalized the equation for the Riemann the tensor. We only had two dimensions, right? We found four non-zero components of the tensor. We contracted that by changing this index to be equal. We did all this, bada bing, bada bong. We found two non-zero members of the Ricci, the tensor. So the question is, why do I have to go through all of this when I can just do this? Why not? When I first started this, I asked exactly the same question. And the answer was, if the Riemann tensor is zero, the Ricci tensor is zero. So that means it's not curved. So there is no Ricci the tensor, and the manifold is not curved. If the Ricci tensor is zero, the Riemannian tensor is not necessarily zero. This is called Ricci flat. And there's a very famous example of this that we're going to look at right now. So this is the relativity the calculator online that I've told you about before, ChristoffelSymbolCalculator.com it's called. And this lad here has done a marvelous job with this. All right. So what we're going to look at is this is the famous Schwarzschild metric. Okay. So the concept is you're far away from, let's say there's a massive gravitational field here. You're far away, you're coming in, that distance is r, right? And at some point, there is a sphere around that massive gravitational field called the Schwarzschild, the radius, that's this, r sub s, of which once you cross that, there's the point of no return. You can't escape. If it's massive enough, it's a black hole and not even light can escape. Okay, so here is the Schwarzschild metric tensor, okay, in four dimensions, obviously. And you plug in what you want to calculate, and it does it. I love this thing. It saves so much work. Okay, it's got a whole bunch of Christoffel symbols. You see them there. It's got a whole bunch of Riemann the tensor components. You see all these here. Now look at this. Oh, what the hell? How can you have all this stuff and contract it all out and you get nothing? Well, because this tensor is used in Einstein field equations and it relates to what's on the other side of the equal sign, which is the stress energy momentum tensor. So if there is no energy or mass stuff, if there's no stuff in the space you're in, there is no energy stress the tensor. Its components are zero. Okay, so that's what this implies, is that the the void you're in has curvature, but there's nothing in it. And so as you approach that black hole or whatever you're going toward, that's massive gravitational field, the curvature is increasing, but there's still no stuff there until you finally get to it, and then you would have to solve this, which is As far as I know, virtually impossible. Okay, so that's why you can have one without the other, but you cannot have, if this is zero, this is always zero. If this is zero, this is not necessarily zero. Okay, I hope that answers your question. It was a good one. See you later.